Hello, so today we are doing this problem called getting two gates, and so let me explain this problem for a minute. So let's say we get a couple of values. We get -1, which represents a wall or an obstacle, and then we have 0, which represents a gate, and the value infinity represents an empty room. And so we get a 2D grid like this one that has the values, for example, infinity, which means there is an empty room here. -1 means there is a wall here, 0 means there is a gate here, and you get the idea. This is the 2D grid representation that we have. And the goal is for each empty room, we want to put, instead of infinity, the number of the shortest distance for it to get to a gate. And so, for example, for this infinity, the shortest distance to get to a gate is, it can't go to this gate, the value 0, which is the gate, because there is a wall between them. But it can get to this 0 here with distance 3. And so our goal is to return the values filled for each empty room. So for this, the value is 2 because there is just this one. It just needs to go through from itself and go to this one and then reach 0, which is distance 2. And so this says that each empty room needs to have the shortest distance it gets to some place. And so what we want is just the shortest path in a way. And so whenever the problem says we need to get the shortest path, we need to directly think about doing BFS, since that's one of the main things that algorithm is good at. And so let's see how can we apply BFS for this problem. And so the way we can think about this is, okay, let's just take every empty room and traverse it and do a shortest path until we get, so basically take every empty room and find the shortest distance to the nearest gate, right? That would give it, that's exactly what we are doing. And since we are doing BFS, we will do level by level, and so we will reach the nearest gate first. But one thing to be aware of is that there are more empty rooms than gates. So you can see that in my example here. So that means that if we do a BFS for every empty room, that would be really expensive. But since we know there is just a small number of gates, basically finding a short distance if we find a short distance from x to y, that's the same thing as finding the shortest distance from y to x, right? So we can just reverse this. So instead of finding the shortest distance from rooms to gate, we can find shortest distance from gates to every room they can reach, right? And then we can just do BFS from gates, and just take from gates, and every time we find an empty room, just put the distance that we have, because if we start from a gate and then we can do that, at that point we can BFS from gates and fill the values for each empty room. Fill the values for each empty room, right? And so, but you can think, okay, so let's say I reach it from this one first. Let's say I started with this gate first, and so it will fill this one with the value 0, 1, 2, 3. So it will fill this one with the value 3. But this one, 0 is closer to it, right? So when we try to fill with 0, how can we know that we need to update this one to 1? We can just look at the distance. If it's smaller, we just update, right? If it's smaller, we can just update the value to the smaller distance. And so BFS from gates, so we can do, for example, BFS from each gate, and if distance if new distance is smaller, just replace, unless it's a gate or a wall, because we don't want to update that, right? And so let's code this up and see what we can get. And so let's see here. So what we need to do is just have, so first thing we know that is if the length of rooms is 0, then we have nothing to do, so we can just return. We can just return rooms, right? But if the otherwise we can continue our algorithm. And so the first thing we want to do is look for the gates and then start a BFS from each one of them. That's what we said here. And so let's just call this def. Let's just do it like this. So we can just go through each row and column, right? So row are in the range of so for row in range of length of rooms, for column in range of basically row base, or let's just make this length of rooms 0, and then we can check if rooms row column is equal to 0, which means a gate. It's a gate. Then we start BFS, right? BFS from gate, which means from row column, and pass this rooms here, or let's just, yeah, that's all we are going to do. And so let's start our BFS, and so BFS from row column. So let's call these I and J to make this simpler. And so now let's do our BFS, normal BFS. So we need to queue the values. And so we do normal BFS here. So collections, let's use our DQ, and we'll start out with these two, with this position, IJ, and the normal BFS template, which is checking while the queue is not empty. We're going to pop the value, which in our case here, the first value is pop left, is obtained with pop left, and then we will need to have, at this point, we'll have so at this point we would have row and column, which are I and J here. And then what we need to do is obtain the direction, so we can go left or right or up or down. So we need something for the directions that we can go to. And so our directions would be directions, let's call them. So that would be, in our case, it would be 0, 1, 1, 0, 0, -1, -1, 0. And so we need to go to all directions to get the neighbors of this row and column position. And so that we can do with directions like this. And then, well, the neighbor like row and the neighbor column would be row plus D0 and column plus D1, so that it gets us this value and this value. And then once we get that, we'll check if it's like in the right boundaries. So, and then length of rows. So this is just normal BFS on a grid, and so in column, and this is the length of, actually this is rooms, and this is rooms 0. And one other thing is that if we encounter something like if we encounter let's say if we encounter a wall, then we shouldn't go, because we can't go there. So let's just say that. So if our rooms and column, so the neighbor has to be different than -1. We don't want to go through a wall. And something else, which is with BFS, we need to check that we haven't visited this place yet, because if we visited it and we visit it again, we might run into a loop there. And so how can we check that? So we can just check if so how can we check that? So one thing we can think of is since this method here, the goal is for what do we want this method to return? So with this method, we want to return just the nearest distance to actually, there is another way we can check visited. So basically, since we know that if we visit a node, we will update it, and so we can just check that we haven't, that it's not -1 and it's not 0. And so we can do that by checking that. Let me see, how can we? So yeah, we can just actually just check if it's different than basically this infinity, which means it was already updated. So if it's different, then let's just initialize infinity, which is just in our case here in Python is just this value here. So let's just say inf equal to this, and then to make this more readable, let's call this gate the value 0. And so here we can check gate. And here, so another thing that I forgot to do is basically here I'm doing for each gate, right? But that's not necessary. I can just do it for all gates at the same time. That way they will be moving at the same pace, since BFS does level by level. And then that way this one will reach this one first, and so I don't need to check the distance if it's smaller, because this one would have reached the next one first, and so it would have updated it first, and so the value would be different than infinity. And so how can I implement that? So in order to implement that, I can just move my BFS. Instead of doing it here, I can just move my BFS here, and then this queue here, I can initialize it this way, and then right away add this. Basically append this for each gate, and then now they will all be initialized to all the gate values. And basically that way I will start out with from each gate, and then they will go at the same time, since we are doing BFS, since they start out in the queue, will go at the same pace, and the first one that updates an empty room would be the nearest one, right? And so at this point, if it was updated, it will not be equal to infinity. And so what I'm interested in, now is only empty rooms. And so I need it to be in the boundaries, and I need it to be empty rooms for me to continue, because otherwise it's either a wall or a gate, or it was already updated by a closest gate to it already. And so if the conditions are valid, and this one is something worth looking at, then I can just update the rooms, since I need to update rooms. And so I need to update the value with the closest to it. So rooms for neighbor values is now the value from row column, its neighbor, +1. Because if for a gate the value would have been 0, so the first one it will go to and update would be 1. And so the next one that will go to that would be 1 + 1, which is 2. And you keep doing that until you reach all the empty rooms, right? And then once we do this, we need to add this neighbor to the queue so that its own neighbors get processed. And so we need to have append nr and nc. And since the value is no longer infinity, we won't go to that exact same node again, or is that same position again, right? And so yeah, that's about it. And then at the end we will have updated all rooms and we can just return them. And yeah, so this passes, this equality check here passes for this grid. And so essentially the idea is we thought first, okay, this is a short distance problem because we want to update each empty room with the closest gate to it. But we noticed that we have too many empty rooms but few gates. So we thought, okay, since it's the same thing to obtain a shortest path from x to y, is the same thing as obtaining a shortest path from y to x, why not just reverse and make the BFS do smaller number of things first? And additionally, we thought also, why not just pick each gate separately and do a BFS for it? But that would be like 2, for example, and there is no reason to do that. And then we would have to check like for each empty room if we can do better with the new gate. And so instead of that, we can just add them all as the same starting point in the queue, and our queue will keep processing level by level. And that way, basically, every empty room would be reached first by the closest gate to it. And that way, we don't need to do multiple passes. We can just do one pass and update as we go along and return the value. And that's essentially the gist of this solution. And this is its solution using BFS. So this is using BFS. Let's see quickly how can we do the same thing using DFS. So we can do the same thing using DFS, except since with BFS we were guaranteed that we won't reach an empty room. We will reach an empty room only the first time by the closest gate to it, because we are doing a BFS. With DFS, we don't have that guarantee, because DFS starts from a gate and goes all the way until it can't reach anything anymore. And so with DFS, we need to do something slightly different. We need to look at each, even if an empty room has already been updated and it's no longer infinity, we need to look with our current DFS if we can do better. If we can do better, then we need to update again. If we can't, then we leave the value. And so that's how can we implement that with DFS. But essentially we will be doing the same thing as this check here, except what we will be doing here is we will be starting individual DFS. It doesn't make sense to add them all at the same time to the queue, because DFS will just go all the way. So there is no like real value in doing all of them at once. And so we'll go one by one, and let's just take these values here. And so we'll go one by one. That means basically that for rooms we'll start with this position, and the distance starts out as 0. And we'll define our DFS that takes rooms, I, J, and the distance, right? And we will check first for if we are still in the boundaries. If we are not in the boundaries, we will just terminate our DFS. And so that means if I is less than 0 or I is bigger than the length of rooms, bigger or equal actually, or J is less than 0 or J is bigger or equal to the length of rooms 0, or okay, or what could happen? So if the value at this empty room is bigger than the current is smaller than the current distance, that means that even for the element after it, it will still be smaller, so there is no needing to continue. And so we can just check if the current value at I, J is less than the distance. So that means that we already have a better value. There is no need to continue, because the one after will also have a better value, because we'll just keep adding 1 to this distance. And so at that point, just return. There is no need to continue. Otherwise, that means that if we get here, that means that these boundaries are correct, and that means that here room G is bigger or equal, right? So that means that this distance is better, so we need to update with it because it's better, and we are looking for the smallest one. And so we need to update with the new distance. And then we need to go to the neighbors of IJ. And so with that, to go to the neighbors, we can just do plus 1j, that's one neighbor, and the distance increases by 1 since we are passing through ij, and then ij plus 1, that's the second neighbor. The other neighbor is I minus 1j, and then another neighbor which is j minus 1, ij minus 1, and the distance each time increases by 1. And we are doing our DFS here on row and column, and at the end we can just return rooms because we updated it with this here, right? And so let's try and see if this passes. So this also passes, and as you can see here, it's the same, almost the same thing as this BFS. We are still going through the neighbors. I could have used their directions, but this essentially is the same thing. And the only difference is that instead of going through the gates all at once, we are going through them each by one with DFS. And instead of just, because we have the guarantee of BFS that we always get the best value first, we need to check if we have a new better value and update. And that's essentially the difference, but both can be solved with BFS and DFS. Yeah, and that's it for this problem. See you next time. Bye.